Hello, I welcome you all in this lecture related with the subject failure analysis and prevention. Earlier this course was of the 8 weeks which was primarily focused on the fundamentals and the general procedure of the failure analysis. Now an effort has been made to extend this course from 8 week to 12 weeks, and in this extended portion of this course we will be talking about the failure analysis of the products made by the common manufacturing processes like casting, welding, forming. So, in this first lecture initially we will be starting with the failure analysis of the castings. So, you know that the castings are made of the variety of materials like the aluminum, cast iron, steels. So, we will try to take the case studies related with the failure analysis of cast iron, aluminum and the steels accordingly. And we will also be talking about the strategies which are used for controlling the failures or minimizing the failures of the cast components during the service. Okay, so starting with this lecture, this lecture primarily focuses on the failure analysis of the castings, and efforts have been made to identify what are the unique factors and features related with the casting which encourage the defects and eventually failure of the castings during the service. So, as far as the main components are concerned, we will be talking about the introduction part of the castings, which is basically about the unique features associated with the castings, then fundamental causes of the casting failures, the common casting defects which will be leading to the failure, and general strategies which are used to avoid the failure of castings. So, if you see the castings, for the casting of any component, what we follow the general procedure is take the metal of the desired composition and the that using the suitable furnaces that is brought to the molten state, and after proper treatment of the metal to have the desired molten metal quality, the molten metal is poured into the mold, so that the defect free casting is achieved. But you see, whenever the procedure of the casting is not appropriate or it is unsuitable for a given metal or given design of the casting, then it leads to the variety of defects. And if the defects are detected, certainly the efforts can be made to repair or discard the casting, but many defects are left unchecked, undetected, and which eventually lead to the failure of the castings during the service. So, if we talk about the major the unique features related to the casting, like castings, if it is very sound, then it to a great extent it performs well, but if the casting is not sound, it means it is having some discontinuities and defects which are beyond the acceptance limit. So, say the common defects like the porosity, inclusions and cracks, whenever these defects are present, they will be reducing the load carrying capacity, they will be increasing the actual stresses acting in those areas wherever these defects are present. Okay. So, how to quantify how much increase in stress that will be occurring in presence of the defects? There are two ways by which the failure is encouraged due to the defects in casting. One, presence of defect reduces the load resisting cross sectional area, that is one, and the second, whenever the defects are present, they will be increasing the actual stresses due to the stress concentration. Okay. So, how much increase in stress concentration is taking place? If you want to see, you can see simply this equation, where you can see the maximum stress acting is equivalent to almost double of the nominal stress, and further it is being affected by the the size of the defect, and the tip radius of the discontinuity, rho t, and square root of this. So, the thing is, the size of the discontinuity and the radius of the defect uh, tip or wherever the defect is present, that radius of that defect on the minimum side is especially important. Say we are having a defect of this size, so the tip radius of this is more important rather than other side wherever the tip radius is more, because the finer tip radius will be causing the greater stress concentration. Okay. So, the presence of the defects in the castings significantly affects the performance of casting, okay, by reducing the load resisting cross sectional area or by increasing the stress concentration wherever it is present. Another important aspect is the microstructure. Microstructure of the casting needs to be controlled. So, if depending upon the casting process, we may get variety of the microstructural features, like in case of sand mold castings, we usually we get the coarse grain structure which occurs due to the low cooling rate, while in die castings we get the fine grain structure due to the higher cooling rate experienced by the molten metal during the solidification. Okay. So, but still again it will depend upon the size and the volume of the casting and actual cooling rate being experienced by the molten metal. If we see the typical these features, so the of a casting, say this schematic shows that skin of the casting experiences extremely high cooling rate, and that is why very fine and equexed grain structure is obtained at the surface. Thereafter, you may have the columnar grains, dendritic grains and the equexed structure. So, there will be lot of heterogeneity in terms of the morphology or the shape of the grains which are obtained in the cast components, and this heterogeneity in the structure affects the mechanical performance and the other desired performance of the castings. Okay. There is also possibility, depending upon the metal, high cooling rate may lead to the formation of the hard phases, while low cooling rate may result in the soft phases. So, not just the grain size and the shape is affected, but the formation of the soft or hard phases are also affected by the cooling rates experienced by the casting during the solidification, and this variation can be observed right from the surface to the center of the casting. Okay. Another important aspect related with the casting is which adversely affects the performance of casting is the segregation. Segregation is about the enrichment of the certain elements in localized manner, that is called normal segregation. In inverse segregation, like there is a depletion or deficiency of certain elements in the castings. Say if we consider, say this is the grain boundary here, this is the grain 1 and this is the grain 2. So, when the enrichment occurs, then this boundary area will be having the higher concentration of certain elements. Okay. Mostly these are the low melting point phases which are present at the grain boundary area, or the elements which are being rejected in course of the solidification or during the solid state transformations. Okay. So, this is the normal kind of the segregation where, and if we do the analysis of such kind of the components, we will find that from the point P to Q we will be noticing the variation in the concentration of the elements like this. So, this is the grain boundary area, this is location P, this is Q. So, enrichment will be observed, but if there is a deficiency of the elements at the grain boundary, then that will be the inverse segregation. That deficiency will be leading to the reduction in the concentration of the certain elements at the grain boundary. So, that will be the inverse segregation. So, if we notice that the performance, mechanical performance, tribological or corrosion performance of the castings significantly governed by the microstructural homogeneity and the homogeneity of the composition. So, if the composition and the microstructure are uniform, then the performance of casting will be really excellent, but if there is a heterogeneity or the segregation tendency, then there will be the segregation tendency of will not just be leading to the compositional variation, but also the microstructural variation, and these in turn will be leading to the reduced performance of the casting, and which as per the application may affect the mechanical performance, tribological performance or the corrosion performance. Okay. Now, the other three important aspects related to the castings is like mechanical properties. Castings do not perform as good as that of the rolled products. Okay. So, rolled products are the formed products which experience the plastic deformation either at the room temperature or at a high temperature. Okay. So, the performance of the castings may be different from those of the formed products. Similarly, the geometrical features, which means the castings may experience the distortion or or difficulty in achieving the desired the geometry or the shape. Certain metals of the higher thermal expansion coefficient experience the greater residual stresses. So, if these residual stresses are tensile in nature, then they adversely affect the performance of casting, especially under tension or under the fatigue conditions. So, if we see here this one, the mechanical properties of the casting, in general tensile strength, which may be in terms of the yield strength and ultimate strength or percentage of ductility. So, these properties actually in case of cast products are little lower than the other types of than the components made by the other approaches of the manufacturing like forming. But if we see the toughness, like say the hardness in terms of the Brinell scale or the Rockwell scale, or the toughness in terms of the Joule obtained through the Charpy or impact test. So, those are actually lower in case of the cast components as compared to the products made by the other approaches of manufacturing. And you know that due to the increased tendency of the defects in casting, higher hardness and the reduced tensile properties and ductility, these actually promote the lower fatigue resistance, greater tendency of the fatigue failure. And if the castings are having the fine grain structure, performance will be, creep resistance will be lower. If the casting is having the coarse grain structure, then the performance of casting under the creep conditions will be better. So, since the casting, the microstructure including the phase and grain structure are significantly of the castings are significantly affected by the cooling conditions and composition during the casting. So, variation in cooling conditions during the casting in different zones lead to the variation in composition and microstructure, and which in turn leads to the heterogeneity in terms of the performance of the casting, mechanical performance of casting. As I said, the cast components, you see the components being made by the casting may have variety of the geometrical features, which may be like in one section it is very thick, another section it is very thin, in one section it is very flat, another section it is very curved one. So, we may require the variety of the geometrical features with internal features or just external features, solid component. So, the varying the section thickness, okay, variation in section thickness and the geometry, these two lead to the differential contraction during the solidification, no, during the solidification or during the cooling after the solidification. Okay. So, a differential contraction during the cooling after solidification leads to the development of residual stress. These residual stresses especially lead to the change in the geometry and shape of the cast components, which may go beyond the acceptance limit, and that eventually will be leading to the rejection. Similarly, the other undesirable features, you see the distortion being caused by the residual stresses, but other geometrical features which may arise due to the poor procedure being followed during the casting, like buckling means the expansion of the mold due to the excessive molten metallostatic pressure, or poor mold strength, swelling is the same, and the red tell. So, all these are basically due to the poor molding sand characteristics. If that is the case, then it will be leading to the change in shape of the mold, and change in shape of the mold will be leading to the change in shape of the casting which is being produced. Okay. I have already said about the residual stresses. So, basically the residual stresses occur due to the differential a contraction during the cooling. Okay. So, one section is contracting more than the other section. If everything is happening in unrestricted way, then there will not be any residual stresses. But if the geometry of the component is such that the contraction is resisted by the mold, in that case it leads to the development of the residual tensile stresses, and it can also lead to the residual compressive stresses, which is considered to be favorable, but that happens little less. And whenever the residual tensile stresses are there, these residual stresses stresses are considered to be the harmful for the static load carrying capacity of the component or casting under the tension. Okay. So, the tensile load carrying capacity of the casting is reduced. Okay. And similarly, it also promotes the stress corrosion cracking. If the component castings are exposed in the corrosive environment in presence of the residual tensile stresses, then this promotes the SSC. Okay. So, these are the unique you can say the features related with the casting, which make it different from the products made by other manufacturing processes. So, now we will see what are the common issues and the defects which are encountered in casting, and which, if these defects if left undetected, unchecked, and the component is put in use, then that will be leading to the premature failure. Okay. So, the failure of the casting is promoted by the variety of defects, and say the one and which is very predominant one is the gaseous defects which are observed in the casting. So, this is just one typical one where the gaseous defects are of the spherical family. This is one, the shape is usually of the spherical family. So, that is what we can see here, but here if these the gases are blocked in like this. So, this gives the feeling like worm. These are called wormhole or worm porosity. Okay. And these gaseous defects will primarily be occurring due to the presence of the gases in the melt or the molten metal inside the mold during the solidification actually. So, we expect that these gases will finally be escaping in course of the solidification and rendering the solid defect free casting. Okay. But if this does not happen, then the gases which are there with the molten metal, they will be leading to the development of the gaseous defects. So, there are many factors which promote the gaseous defects, okay, in the casting, and one of the like a few of these major factors are like, in case of the sand mold casting, if the moisture is too much, then the moisture in the mold, if this is excessive, then as soon as the molten metal is poured in, the moisture evaporates, and that goes with the molten metal. Okay. And if the cooling rate is extremely high, then solidification time will be very less, and these gases or the vapors will not be able to come out, which will eventually be leading to the formation of the gaseous defects. This is one. Second, if the gases are too much and if your venting is not proper, like the mold which has been designed does not have much provision for the venting of the gases and air. Okay. So, venting holes are made. If that is not appropriate, then these gases will also be get entrapped with the molten metal. That is the another one. The third one, the provision which is made in the mold is this, where the mold should have the enough capability to allow escaping of the gases through the mold wall. So, for that the permeability of the mold must be high enough, and if the permeability is good, then the gases present in the molten metal, wherever from they have come, either due to the large difference in the leak or the gases were already dissolved in the molten metal, or degassing process was not proper, or inappropriate molten metal, the melting has been done in inappropriate condition, improper melt treatment has Then there are many factors which can cause the excessive presence of the gases in the molten metal, but it is expected that these gases will be escaping finally from the molten metal during the solidification, and for that permeability of the mold must be good, but if the permeability is less due to the variety of regions, say the grains are very fine, sand grains are very fine, or excessive ramming has been done where too much packing leads to the reduced porosity between the particles, sand particles in the mold, and that eventually leads to the reduction in permeability. So, enough efforts must be made to ensure the proper permeability of the mold, so that the gases being released in course of solidification they can escape. Solidification time is the another factor which promotes the which affects the gaseous defects, and this the solidification time, if it is long, then the gases being rejected in course of solidification will have enough time to escape, and so the tendency for the formation of gaseous defects will be reduced, and a few degassers are added in the molten metal for the molten metal treatment, so that the gases dissolved in the molten metal can escape. And the likewise the gating design also should be such that it allows proper venting and the feeding of the molten metal in proper conditions, so that the gaseous defects can be reduced. There is another important factor which affects the gaseous defect is the difference in the solubility of the gases in the molten metal, or in the melt in, or you can say molten metal in liquid and solid state. You see, the different metals show the different kind of the solubility difference in liquid and solid state. So, if a metal showing the greater difference in the liquid and solid state solubility to a particular kind of gas, then means in the liquid it can dissolve large amount of the gases, but in solid it can only a small volume of the gases can be dissolved in the solid state. If this difference is large, then this will be encouraging or promoting the gaseous defects, because large volume of the gases will be released during the solidification and these must escape, otherwise it will be promoting the gaseous defects. So, the greater difference in the solubility of the gases in a metal in liquid and solid state promotes the gaseous defects. Okay. So, this is about the gaseous defects, and basically optimization of the proper moisture, proper attainment of the permeability, and depending upon the case, maybe preheating may be done for enhancing or having the suitable solidification time, proper degassing, and optimum gating design for ensuring the escaping of the gases. The another type of the casting defect is like inclusions and the cracks. These are primarily promoted by due to the interaction of the molten metal with the gases. This is one. These gases are usually in form of oxygen, nitrogen or hydrogen. Okay. And another is like when the chemical reactions take place between the elements which are present in the molten metal, like iron is reacting with the sulfur and forming the low melting point iron sulfide. So, these kind of these gases may be reacting to forming their oxides, okay, nitrides, and these oxides and nitrides, if having the density similar to that of the molten metal, then these will be retained by the molten metal. They do not float or settle down easily. If the larger difference in the density of the oxides and nitrides with the molten metal, then it will lead to the either floating or the settlement. So, if it settles down, then this is the natural can say removal, and if it floats over the surface, then it can be removed as a slag. So, that is good. But if it does not happen, if the oxides and nitrates being formed are having the similar density as that of the molten metal, then it will lead to the uniform distribution or the presence of the defects, the presence of inclusions in the casting. Okay. The formation of the low melting point phases, as I have said, reaction of the like either the lead is present uh, like in free machining steels, or sulfur is present also in free machining is steel. So, here this will be forming the low melting point constituents, and during the casting when these segregate at the grain boundary and in presence of tensile stresses, segregation of these low melting point things promote the hot cracking and the tearing in presence of the low melting point phases. Sometimes the properties of the castings are degraded heavily due to the formation of the hard and brittle intermetallic compounds. Okay. So, these are called IMCs. If the hard and brittle IMCs are formed in the castings, then that will be increasing the hardness, but at the cost of toughness and ductility. So, those may be unacceptable for engineering applications. So, if that is happening, then this will be leading to the reduced performance of the casting. So, here in this as far as the chemical reactions are concerned during the casting and the formation of oxide nitrides. So, these will be breaking the metallic continuity. You see, formation of oxide nitrides will be breaking the metallic continuity. So, here say this is the metal matrix of the casting, and here you have inclusions of the non-metallic oxides and nitrides. These will be breaking the metallic continuity. So, these will act as a site for the stress concentration or site of the weakness, where from the voids will nucleate, cracks will nucleate and promote the failure. Okay. The low melting point things this will be promoting the cracks actually. So, very fine cracks in the casting, especially in the areas where residual tensile stresses are being developed, that will be promoting the hot cracks. So, the phosphorus, lead and the sulfur promote the hot cracking. Sometimes addition of the manganese actually in iron castings or steel casting, cast iron castings help in reducing this cracking tendency. Okay. And this is also the compositional issue where the hard and brittle IMCs are formed, and that will be adversely affecting the performance of casting. Okay. So, next another major factor which affects the or which dictates the casting defect significantly is the molten metal quality. So, there are two aspects related with the molten metal quality is the appropriate temperature at which the molten metal is being poured into the mold or in the gating system. If it is too low, then it will be a too low temperature will be causing the higher viscosity, higher surface tension, and that in turn will be reducing the flowability or fluidity of the molten metal, and which will make the filling of the mold difficult, and if it does not happen effectively, then it will be leading to the defects like cold shut or misrun. Okay. And if the molten metal temperature is too high, then this will be making the molten metal of the very low surface tension, low viscosity, and so your molten metal will be easily be able to penetrate into the finer details of the sand particles during the casting in the mold, and that in turn will be leading to the penetration the rough surface of the casting. So, another important thing another way by which the high temperature will be affecting the casting is like increasing the temperature increases the solubility of the gases. Okay. And increasing the temperature also affects the reactivity of the metal with the gases. So, both these will be increasing the oxide or nitride formation as well as the gaseous defect formation. So, increasing solubility will be promoting the gaseous defect formation. On the other hand, if the temperature is increasing, then its reactivity with the gases present will increase, and that in turn will be leading to the increased inclusion formation due to the formation of the oxides and nitrides. Okay. And what is the reason behind all this? Like either the molten metal temperature has not been appropriately controlled at the time of pouring, that is one, and the second the proper melt treatment has not been done, which means the impurities has not been filtered properly. Okay. The degassing is not proper, and therefore, lot of gases are there with the molten metal, and the fluxing is not proper, alloying is not proper. So, means the melt treatment has not been done properly, or the molten metal temperature has not been controlled properly, and both these constitute heavily to the poor quality of the molten metal, okay, which will be increasing the inclusions, cold shut, misrun and the penetration and the shrinkage cavity. Then the poor molding sand, which you see, molding sand is supposed to offer the certain characteristics which may be in terms of the refractiveness, hot strength and permeability, collapsibility. So, these are the characteristics which a molding sand should have, but if it does not, then it will be leading to the many undesirable changes in the mold itself. No, so because our molding sand is poor, if it does not have the desired set of the properties, then it will be changing the geometry of the mold itself, one, okay, due to the high temperature or the pressure of the molten metal conditions being experienced by the mold during the casting, that is one. The second, if the permeability, if the molten metal permeability is less, then it will be leading to the reduced possibility of the gases to escape from the mold during the solidification. So, that will be promoting the gaseous defects. So, the point here is cuts, washes, buckles, fusion and cracks. These are the issues which are observed, and these occurs primarily the cuts, washes, buckles. These three occur primarily due to the low green strength, low hot strength. Okay. Then the fusion leads to the fusion is caused by the melting of the surface layers of the mold due to the poor refractoriness of the molding sand, okay. And the gaseous defects are caused by the poor permeability, and the poor collapsibility leads to the formation of the hot tears and hot cracks, because after the solidification, when the casting is shrinking due to the drop in temperature, the casting is shrinking, it develops the compressive stresses, but if the molding sand does not collapse, then it develops the tensile stresses. So, the casting which is shrinking, if shrinkage is not allowed, then it leads to the tensile stresses and which promotes the hot tears, okay. And so, this is important, that the collapsibility, the molding sand must collapse, and another useful way of another important aspect of the collapsibility is how easily you can take the mold after the mold, or how easily you can take the casting out of the mold by breaking the molding sand, okay. So, the poor molding sand characteristics poses many challenges. Many of these factors affect the soundness of casting, and which in turn affects the performance of casting during the service. The residual stress, as I have explained, due to the differential expansion and contraction being experienced by the casting during the cooling after the solidification, leads to the development of the change in shape, leads to the change in shape of the casting in form of distortion, hot or the cold crack and stress corrosion cracking, and this is promoted especially when the thermal expansion coefficient of the metal, casting metal, is very high, or the faulty design of the mold or the core, and the poor collapsibility, as I have explained. So, the casting defects due to the poor gating systems are which are promoted primarily due to the like excessive turbulence being experienced by the molten metal. Poor gating system design can lead to the multiple issues like turbulence, poor infiltration, short or long filling time, or lack of directional solidification. And if these issues are there, then it will be promoting the inclusions, piping defect or shrinkage cavity, okay. So, a proper gating system has to be designed and to make the sound casting. So, let me elaborate this little bit. Turbulence will be increasing the possibility of interaction of the molten metal with the gases, okay, thereby increasing the tendency of the inclusions and the dissolution of the gases in the molten metal. The apart from damaging the mold wall due to the excessive turbulence. Then the filtration, the impurities present in the molten metal must be filtered out, and if it has not been done properly, those impurities have not been removed properly, then it will be leading to the presence of inclusions and defects in the casting. Short and long time of the casting filling time. Short filling time will have the tendency to damage the mold walls due to the excessive turbulence and sudden impact of the molten metal streams, and the long filling time may lead to the misrun kind of the defect, where in one section the solidification is started while another section where the molten metal is yet to be filled in. The lack of directional solidification, which is actually desired most of the time, but if it is not there, then it can promote the piping defects or the other gaseous defects in the casting. Okay. Then unfavorable metallurgical reactions like cold and hot cracking, poor toughness. So, the lack of graphitization in the cast iron castings, wider solidification range promotes the hot tearing, and the hot and soft spot formation is observed in case of the hardenable ferrous metals, particularly say cast iron or the high carbon equivalent steels. Then what are the strategies to overcome these issues is like work on the proper quality of the molten metal which is being fed, design the gating system in such a way that molten metal can be filled in the mold in the minimum possible time without turbulence, without encouraging the interaction of the molten metal with the gases, and it has enough permeability, enough the runner and the in-gate systems to fill the molten metal cavity smoothly, and proper riser design so that it can feed the molten metal to the mold to compensate the shrinkage of the molten metal, and to develop the favorable cooling conditions so that desired microstructure and metallurgical features can be achieved, and try to have the directional solidification. So, the internal defects are avoided and the desired and piping defects are avoided to make the sound casting. Okay. So, as let us summarize this lecture. So, in this lecture particularly I have talked about the unique features which are offered by the casting, the common casting defects which usually lead to the failure of the castings during the service, and the causes and the mechanisms leading to the variety of defects, and what can be done to overcome the issues related with the casting defects. That is all. Thank you for your attention.